Welcome back. If you're new here, I'm learning ultra low latency C++ for quantitative finance. In part 1, we took an intentionally horrible C++ web server and optimized it using zero parsing. In the end, we hit around 8,700 requests per second. But then we hit a wall called TCP IP OS stack. We tried running our original optimized version on multiple threads. However, we couldn't go beyond the 9,000 requests per second. Today, I'll show you how rebuilding the blocking architecture into a non-blocking state machine pushes this exact same server up to around 60,000 requests per second. Just to backtrack, when my single-threaded server maxed out, the obvious next step was to just add more threads. I linked pthreads and spawned one listener loop for every hardware core on my machine. To make this work, I used the SO reuse port socket option. This tells the Linux and macOS kernels to allow multiple server sockets to bin to the exact same port. The operating system then automatically load balances incoming connections across our worker threads. But in the end, when I ran the stress test with heavy payloads, the throughput barely moved. Why? Because our sockets were still blocking. Even with multiple threads, each thread was entirely held hostage by one connection at a time. If a client was slow, the CPU core just sat there sleeping. To hit the 60K, I had to tear this down and start over with a non-blocking architecture. I started by stripping the server back down and making the listening socket completely non-blocking using this function. Instead of waiting for data, I used Kqueue to let the server sleep until the OS explicitly told us a socket was ready. But this introduced a completely new problem. What happens if a client sends a massive JSON body, but we read 4 kilobytes before the socket says E again? If we try to parse it procedurally, our memory gets corrupted. We had to turn our request object into a reusable state machine. We started out by splitting the parsing into phases. One for header, one for body, and one for writing the response. Now, if the kernel says E again, we don't crash. We just return the not finished state. The connection goes to sleep, and its progress is perfectly safe in the memory, while the Kqueue loop handles someone else. By the way, Kqueue is only available on macOS and BSD derivatives. If you want to see how these optimizations translate to Linux later, hit the subscribe button. And now let's look at the stealthy performance problem this created. Okay, we just built the state machine. However, if our client sends the data slowly, a naive parser will rescan the entire string buffer from index 0 every single time it wakes up. Under heavy load, this turns into O n complexity and ruins our CPU cache. I fixed these issues during parsing by adding state trackers like the header's scanned position. This means that when we resume parsing, we just jump straight at the end of what we've already checked. I also changed how our buffer grows. Instead of resizing the string exactly to the next read size, we grow it geometrically. While this actually consumes more memory, it also drastically reduces the number of heap allocations. Awesome, so now we have an incredibly fast, non-blocking, single-threaded event loop. It's time to scale it back up. Basically, I took the entire Kqueue logic and wrapped it inside a server worker class. We then spin up one of these workers per hardware thread using the previously mentioned SO reuse port flag again to let the OS load balance them. However, this time every thread can process thousands of connections concurrently without blocking. One neat little trick I did there to make it even more hyper efficient is that I don't use hash maps to track clients / requests. Since file descriptors are just integers, we use the raw socket descriptor as the direct array index into a pre-allocated vector of requests. Basically, we know ahead of time that the client file descriptor could be from 1 up until our ulimit. So at startup, we get the OS ulimit and pre-allocate this array of requests. This means that while processing each K event, we can look up the underlying requests with zero overhead for lookup. And to minimize context switches / OS syscalls, when a wave of clients connects, we don't just register them with K event one by one. We batch them into a stack allocated array and then push them to the kernel in one singular system call. This means that at this point, our code is basically as fast as possible for what we set out to do. That being said, I feel like we can squeeze out even more performance out of it. First, I swapped out the default C++ allocator for Jemalloc. It handles highly concurrent multi-threaded string allocations way better by using isolated thread arenas. And secondly, I implemented PGO, Profile Guided Optimization, in CMake. I compiled an instrumented version of the server, hit it with a heavy workload test, and recorded exactly which code paths executed the most. I merged that profile data and recompiled the final binary. Kqueue uses this real-world telemetry to inline hot paths, align instructions with the L1 cache, and move error handling out of the way. And finally, what you've been all waiting for, let's run work one more time. And 58,242 requests per second. This is amazing. We took a naive blocking server, tore it down to a non-blocking state machine, scaled it across the CPU cores, and boosted our throughput by over 600%. I'm actually really glad with this result. All of the code, including the PGO scripts and my macOS kernel tuning parameters, is on the GitHub in the description. But remember, Kqueue is just for macOS and the BSD family. If we really want to get into the high frequency trading space, we need to deploy to Linux. And the good thing is, Linux kernel has something much faster, and it's called IOU ring. This means that in part 3, we're going to rewrite this entire event loop to completely eliminate system calls using kernel submission queues. If you want to see that, hit like, subscribe, and I'll see you in the next one. Bye.